All right, the third quiz is coming up, and it does cover a few calculations involving insoluble salts and Ksp. So let's take a look at this topic. What's this all about? Well, hopefully you remember the solubility rules from Chem 1. It tells you whether or not something dissolves in water. So this first rule tells you, hey, if you have a salt that contains one of these ions, guaranteed it's going to dissolve in water. So if you had something with ammonium in it, say you had ammonium carbonate, will it dissolve in water? You bet it will. Anything that contains the ammonium ion is highly soluble. So these soluble salts, you can keep adding them to water. You can get the concentrations up to 1 molar, 2 molar, 10 molar. You can get real high concentrations. Now, insoluble compounds. These are salts that you put into water, and visually, you can't even tell they're dissolving. It looks like nothing's dissolving at all. So some examples, under your soluble stuff. Anything that contains chloride, bromide, or iodide is soluble unless it happens to be silver chloride or silver bromide or what have you. So things like silver chloride, you drop it into water, looks like nothing happens. It remains a solid. It just sinks to the bottom. Other insoluble things, most things that contain carbonate don't dissolve. So if you had calcium carbonate, CaCO3, drop it into water, it just sinks to the bottom. It remains a solid. So those are the solubility rules. Again, most ionic compounds love water. They dissolve in water, freely dissolve in water. If you have nitrate in your compound, guaranteed it's going to jump into the water, dissolve really well. Any of these, it's going to dissolve really well. But then you have these insoluble compounds. These are the compounds that you typically see as a precipitate. If you recall precipitation reactions where you mix two things together and suddenly it gets cloudy. So for instance, if you took a solution of calcium ions and mixed it with a solution of carbonate ions, put these two things together, it gets all cloudy because it is forming that stuff. Now, here's the deal. Even these insoluble salts, they do dissolve to some limited extent. It's just you don't get a very high concentration of them. Now, for all the calculations we'll be doing, and there's quite a few calculations coming up here, you want to be able to write an equilibrium reaction that represents the solid material dissolving. So, silver chloride. If you had to write a reaction that represented silver chloride dissolving, pretty simple. Silver chloride, solid, you drop it into water, it dissolves to give you silver ions, which are aqueous, and chloride ions, which are aqueous. For this entire section, all the calculations that you have to do always start by writing the reaction for the stuff. It's going to talk about some stuff and say, what's its solubility? What is its Ksp value? How does it behave in the presence of a common ion? All kinds of weird problems. Start with this guy. Start with the thing dissolving. So, if you were to take silver chloride, it's a white solid. It's a nice white solid powdery material. If you were to drop it into a beaker of water, what's going to happen? Well, here's your beaker. Here's the water in the beaker. You take solid silver chloride, drop it in there. Hey, you won't see it dissolve, but it's a white powder. You'll see that white powder sink to the bottom. You'll have this little pile of solid silver chloride sitting at the bottom, but trust me, it is dissolving. Some of these silver chloride molecules will dissolve, and they will form silver ions floating around in the water. And of course, you'll also get chloride ions floating around. Why do we say it's a so-called insoluble compound? Oh, the concentration of these things will never go very high. We're talking really low, like 10 to the negative 5th, 10 to the negative 10th. Some things give 10 to the negative 40th molar. We're talking, if you can wrap your brain around that, 10 to the negative 30th molar, 10 to the negative 40th molar. Those are really, 10 to the negative 30th means 0.0000. You got 29 zeros and then a 1, So they barely dissolve. Visually, you'll never see it. But it does dissolve to give you some silver ions and some chloride ions. Hey, guess what? After it's dissolved for a while, you hit a certain level of these, and these things will start to turn back into the solid. It's an equilibrium reaction. So these processes where the stuff dissolves, they're equilibrium processes. So if you have this solution, if you filtered off the solid, what would you have? You'd have a solution of silver ion. It would contain a real low concentration of silver, a real low concentration of chloride. It would be a saturated solution. So it would be a saturated solution of silver chloride. It would have the maximum amount of silver chloride in it. That does not give a precipitate. If you were to increase the concentration of chlorine a little bit, guess what? You'll start to get the precipitate. The solution turns cloudy. If you increase the concentration of silver ions, that will push the equilibrium. If you increase either of these concentrations, it will push the equilibrium that away. So that's what this whole topic's about, is these insoluble things dissolving. What types of problems are you going to see? 4 different types of problems. The first one is you're given a Ksp value for a salt. Calculate its molar solubility. We haven't said what Ksp is yet, have we? Ooh. Okay, this is an equilibrium reaction. You can write an equilibrium expression, K. For these types of processes, stuff dissolving, we call it Ksp. And it's going to be the concentration of this stuff, concentration of your silver ions, times concentration of your chloride ions. That's the equilibrium expression there, the Ksp expression. So for each of these problems, it deals with this equilibrium, and this equilibrium is governed by this mathematical expression, where this is a number. Oh, the values of Ksp, where do they come from? Got tables and tables of them here. Bottom line is, the lower that number, the less soluble the material. So let's take a look at a quick example here. Barium sulfate, 2.3, 10 to the negative 8th. Barium chromate, 8.5, 10 to the negative 11th. Barium is really toxic. You definitely don't want barium ions in your system. It will kill you. So let's say you wanted to poison somebody. Which one of these is going to be better, the barium chromate or the barium sulfate? The barium sulfate, smaller number, larger number, it is more soluble. Bottom line, even this stuff, that number is so small, even though barium ions are toxic, you can drink a big old solution of barium sulfate, it won't poison you because it just doesn't want to dissolve. A real small number, it really doesn't want to dissolve. So those are Ksp values. You get them from tables. Okay, let's go back to the types of problems we'll be seeing. First type of problem, you're given a Ksp value and you have to calculate its molar solubility. Most textbooks represent the molar solubility with a little s. That's going to be what's the concentration of the stuff in solution in a saturated solution. So if I do this, I make myself a saturated solution of silver chloride. What's the molarity of the silver chloride here? Now, to do these, classic equilibrium problem. Write out the reaction for the stuff dissolving. Make an ice table. Use S instead of X. I noticed the OpenStax book is odd. It uses X. Almost all other textbooks use the letter S. The letter S stands for the molar solubility. What is the molar concentration of the salt dissolved in a saturated solution? Write out the Ksp expression, solve it for S. Quick example here. Find the molar solubility of lead 2 chloride in water. Got the Ksp value. What do you do? Write out the reaction for the stuff dissolving. Lead chloride, PbCl2. That's your solid material. It dissolves to give you Pb plus 2 and 2 chlorides minus 1. These guys are both aqueous. So going from the solid to the dissolved. Make an ice table. What's the initial concentration of it? What's the change in the concentration? What is the equilibrium concentration for that material? So, how do you go about doing this here? The initial concentration of the solid, let's see. In our equilibrium expression, solids don't matter, right? So we don't care. We don't care about that. Now, before any of this is dissolved, none of it's dissolved yet. What's your concentration of lead? 0. Your initial concentration of chloride is 0. How does it change as this dissolves? Make this, instead of saying X, we say this goes up by plus S. This goes up by plus 2S. Why the 2? Because I got a 2 right there. How does it change? Oh, this just stays as S. Or what's the equilibrium concentration? S and 2S. So there's your ice table. So, start by writing out the reaction. Your ice table. Now, what do you do next? Write out the equilibrium expression and solve for S. So in this particular example, Ksp is going to equal the concentration of the lead 2 times the concentration of the chloride. And since there's a 2 here, the concentration of the chloride has to be squared. Plug everything in. We got a number here for Ksp, 0.7 to the minus 5th. So I get my 0.7 times 10 to the minus 5th. Concentration of lead is S. Concentration of chloride is 2S, and I have to square that. Hey, when I square this, I have to square that S. I have to square that 2, so S becomes 4S squared times S. The whole thing is 4S cubed. So this term times this is, boom. Most common mistake people make on a quiz or an exam here is they end up writing either 4S squared or 2S cubed. Be careful with this part where you go from here to here. Don't make a silly algebraic mistake. It's real easy to do if you're in a hurry. So again, That 2 gets squared, becomes a 4. That s gets squared, so this is 4s. This whole term here is 4s squared multiplied by s. That's how we're getting the 4s cubed. So what do we do from here? Oh, you solve it for s. So you'd say you're 1.7 times 10 to the negative fifth divided by 4 is equal to s cubed. And you do the math on that. S cubed is going to be 4.25 times 10 to the negative 6th power. Take the cube root. Take the cube root of that. You get 0.0162. And that is the molar solubility. So at this point you'd say S, your molar solubility is that. In other words, a saturated solution of lead 2 chloride will have 0.0162 molar concentration of lead 2 chloride. So in your saturated solution, your molarity of lead will be 0.0162. Hey, guess what? Your concentration of the chloride ions in that saturated solution will be 0.0324, twice as high. The chloride concentration is twice the concentration of the lead. So that's the first type of problem. They get easier after this, trust me. But the first one, if you have a Ksp value and you have to find its molar solubility, write out your reaction, make your ice table, write out your Ksp, plug everything in, and solve for S. Second type of problem you're going to encounter, another real common type of problem. You have some kind of solubility data. They tell you the molar concentration in a saturated solution. Find the Ksp. So the steps here, write out the Ksp expression, plug in the values for solubility, you're done. Pretty simple one. So our example here. You have a saturated solution of silver sulfate. You find that right there is the molar concentration of the silver ions. Find the Ksp. For this one, of course, Ag2SO4, it's your solid. When it dissolves, it's going to give you 2 silver ions and 1 sulfate solution. So your Ksp is going to be the concentration of silver ions raised to the 2nd power times the concentration of the sulfate ions. If you're looking for Ksp, all you got to do is plug in a number here. Hey, it has a 1.5 10 to the minus 2 concentration of silver. Oh, geez. This is too easy, right? So this guy here, silver, is 1.5 times 10 to the negative 2. You need a number to plug in here, and be careful. It's not this number. But guess what? If you know this value, you can find this value. This number is going to be half as much as this one, right? I'm going to go ahead and work it, then I'll show you how I'm doing that in my head. So the concentration of the sulfate is going to be 7.5 10 to the minus 3rd. crunch out these numbers, and you'll find your Ks. Oh yeah, I almost forgot. Got to square that one there. Right? Again, that 2 is coming from there. So you crunch these out. It's 1.7 times. Now, if you're wondering, how did I know that count? Oh, it's stoichiometry. If I know the concentration of this, I can find the concentration of this. So if I start the problem with the concentration of my silver ions, 1.5 times the negative 2 is my silver concentration. I'll leave the charges off. What's my mole to mole ratio? Oh, I get one of these. I get 1 sulfate for every 2. Oh, 1.5 10 to the minus 2 divided by 2 is that guy. So again, if you know the concentration of one ion, you can always calculate the other one through simple stoichiometry. My guess is, I don't think we give you one that tricky on the quiz, but that's how you would do it. Okay. Third type of Ksp calculation. Predicting when a precipitate will form if you slowly increase the concentration of one ion. Ooh, how do you start? Oh, always write out the reaction for the stuff dissolving. Write out the Ksp expression. Let's do that for this example. What is the maximum concentration of silver ions that you can add to a 0.05 molar solution of chloride ions before the precipitation of silver chloride begins? When you're lost in Ksp land, write out the reaction for the stuff. So silver chloride is what they're talking about, right? So it's KgCl is your solid. That dissolves, it gives you G plus 1 aqueous Cl minus 1 aqueous. Okay, still a little bit lost. Well, we got an equilibrium expression. Write out the equilibrium equation. Say for this process, Ksp is the concentration of this times the concentration of this and the big thing is to realize that anytime the product of these two numbers, this concentration multiplied by this concentration, anytime that is greater than Ksp, it means the equilibrium is shifting to the left. You're making a precipitate. So if the product of these two numbers, multiplying these two numbers together, gives you a number bigger than this, that means the equilibrium is shifting to the left. That means you're going to start getting a precipitate. So how do we do this? Plug and chug. Plug in some numbers. Ksp, 1.6, 10 to the negative 10th power. What is the maximum? We're looking for that. We're looking for the concentration of silver. We know the concentration of the chloride. This is a pretty simple problem, isn't it? Your concentration of the silver ions, you can solve for that easily enough. You know, this divided by the 0.050. What are we going to get there? 10 to the -10th divided by 0.05, 3.2 10 to the -9th. So that's telling us that if we had a solution here, a beaker, our concentration of silver is 0.05, of chloride. We can keep slowly increasing the concentration of silver, keep increasing the concentration of silver ions. Once that concentration hits this number, it'll start to turn cloudy. That's when it starts to turn cloudy, it's right there. So that's predicting when a precipitate will form. You know the concentration of one thing, you know the value of Ksp. When this other thing hits a certain concentration, that's when you start to turn cloudy. That's when you start to get a precipitate. Last type of problem. These, when I was taking this class forever ago, these were the toughies, but don't worry, you're not going to have too much trouble with them. This one is more about the concept of the common ion than anything, but we'll still walk you through how to work the problem. It's calculating the solubility of a salt in the presence of a so-called common ion. A lot of students struggle with, what do you mean by common ion? It is so simple. Look, you got a salt, you dissolve it in water. You get a positive ion and a negative ion. So calcium phosphate dissolves in water. It's going to give you calcium ions and phosphate ions. There's your equilibrium right there. So the calcium phosphate dissolves. It gives you aqueous calcium ions. And for each molecule of this, you also get 3 aqueous phosphate ions. The calcium ions and the phosphate ions are common ions to the compound calcium phosphate. What this means is, if I were to try to dissolve this stuff in a solution that already had some calcium ions in it, so let's say I've got a beaker and maybe I've poured in some calcium nitrate. So it already has some aqueous calcium ions in there. And I try to dissolve my calcium phosphate in here. It's not going to dissolve as well as it would dissolve in straight water. Why is this? Oh, it's Le Chatelier's principle. I've got this equilibrium system, right? If I increase the concentration of calcium ions, I try to raise this concentration up. The equilibrium system is going to try to lower it down by shifting it that way. So increasing the concentration of calcium will push the equilibrium to the left. Same thing if I had put phosphate in here. If I had some phosphate from, say, ammonium phosphate, which is super soluble. So I just throw some phosphate on it. Hey, it's going to push that equilibrium that way. So the real thing to know here, you won't have to solve these types of problems too often outside of Chem II, but you should definitely know about the common ion effect. In the presence of a common ion, stuff is less soluble. So, how do you approach these? Well, when in doubt, write out the reaction for the stuff dissolving. In this case, you make an ice table, write out the Ksp, solve for S. The only thing is here that solving for S can be tricky as all get out, but I'll show you a way to get around that. So here's our example. This one's right out of the OpenStack textbook. I couldn't think of an example off the top of my head. So anyway, what is the molar solubility of cadmium sulfide in a solution that already has a cadmium concentration of 0.010 molar. So write out the reaction. Cadmium sulfide, solid, dissolves to give you cadmium ions and sulfide. That's your reaction. Make your ice table, the initial concentration, the change in concentration, the equilibrium. Again, the solid doesn't appear in the equilibrium expression, so we don't care about that. Not applicable, so to speak. Now, this one's telling us cadmium sulfide in a solution that already has a cadmium ion concentration of 0.01. So he's not starting at 0, he's starting at 0.01. Where did it come from? Hey, maybe somebody threw some cadmium nitrate, which is highly soluble in there. So got some cadmium in there already. Before anything's dissolved, sulfide is 0. This one goes up by S. This one goes up by S. The equilibrium concentration here is going to be 0.01 plus S. This is going to be S. There's your ice table. Okay, set up your Ksp expression. Ksp, we got a number for that. 1 times 10 to the minus 28th. How do they measure that? Guys, that's an incredibly small number. That's 0.00000. It's 27 zeros before you get to anything. So, in other words, this stuff's not very soluble. Oh, good things to know in yellow. Metals, a lot of metals form precipitates with sulfur. These sulfides are typically super insoluble. If you look at your table of Ksp values, the really small ones are usually ones that involve sulfide. Anyway, so your Ksp value is that nice small number, and that's equal to the concentration of the cadmium, concentration of the sulfide. So we get 1.0 times 10 to the negative 28th is equal to 0.01 plus S times S. Hey guys, this is going to be a quadratic equation. It's going to get ugly. Here's how you simplify it. That term right there. We know the stuff's not very soluble. I mean, that's an incredibly small number. So we know that S is a really, really small number. 0.01 plus S is pretty darn close to 0.01. When you go to solve this one, simplify it by saying 1.0 times 10 to the negative 28th equals 0.01 times S. Solve it for S. In this particular one, it's 1 times 10 to the minus 6. In other words, this number plus S, that number plus 1 times 10 to the negative 26 is pretty dang close to 0.01. So we would never give you one where you had to solve the quadratic. They can get really ugly really fast, these problems can. The big thing to know is the common ion effect. If you have a particular compound, it is less soluble in a solution that has any of the common ions in there. So that's the big thing to know. Hope that clears up some stuff with Ksp for you.